And yeah, so hello guys. Today we're going to talk about embedding sharing and into the positional encoding. And a brief reminder that this one is going to be a fairly short meeting post what I planned. I didn't have time to properly prepare for rope, deep dive into rope and alternative ways to encode and maybe not encode anything. There's a lot of research there, and there's even more research in long context, which I want to properly overview, and said I didn't have enough time. And another reminder that unless we have new volunteers to present, we'll have to put the club on hiatus until June because I'm working on a paper. Hopefully we'll have enough time to finish it. Anyhow, back to now and here and now. And here and now we have embedding, sharing, and positional encoding. Crap. And we are back. All right, embedding, sharing, and positional encoding. I should be able to see my screen. So what is it all about? Embedding sharing. As you all know, like in a typical LLM, we have an embedding table and we have the output projection matrix table, whatever you call it. And in a sense, they perform the same function of transforming tokens into embeddings and vice versa. So it's kind of function and its inverse in a sense. And it seems kind of natural to put them, to reuse the same matrix, to share input embeddings and output projection, because like, well, we map in tokens to embeddings, like how hard could it be to share them, right? And it makes a lot of sense. Well, it's called embedding tying, so tied embeddings. And tied embeddings is when we use the same matrix for input and output projection. And it makes a lot of sense, especially for small models. So the guys in the book, they give us this awesome calculator, and you can see that, well, for the amazing screenshot, right, with this download button. But I think it's like for 1.5 billion model, embedder takes like 35% of the model. So if we tie embeddings, we save a lot of space, right? So for separate embeddings, 1.5 billion billion parameter model, 35% of that is embedder. And if we tie embeddings, we save 300 million parameters, which seems like a lot. So cool, good stuff. So where's the poop, Robin? Quoting my favorite How I Met Your Mother. But before the poop, for larger models, it's not that drastic. So for large, like 70 billion model, the embeddings take only 3% of the overall size. So it's embedding time doesn't make that much sense there. So and now to the poop. The guys in the book conducted a few experiments. Well, actually not a few experiments, a proper population study for 1.2 billion model with 16 layers tied. They compared it with 1.2 billion model untied embeddings. And because when we untie embeddings, to match the number of parameters, we have to decrease number of layers. So this is the baseline, 1.2 billion, 12 layers untied. But they also compared it with the 1.4 billion model, 16 layers untied. So basically the same model as we have with tied embeddings, but with embeddings untied, so which makes it a bigger model. And we have kind of surprising results. Maybe not so surprising, depends on your opinion on the embedding time. But this is the lowest curve for 3 options with tied embeddings 16 layers, untied embeddings 16 layers, and untied embeddings 12 layers, which is like the probably the most fair match. And we can see that tied embeddings and untied embeddings, like the number of layers matters the most, and like tied and untied embeddings produces roughly the same result for the small model. And when we take a look at the property vals, we can see that tied embeddings sometimes even outperform untied embeddings with 16 layers. So basically, smaller model with tied embeddings outperform bigger model with untied embeddings. And by bigger model, we once again mean not the number of layers, but number of overall parameters. With the only exception of open book QA, which I think it's like, well, God knows what's happening there really. Else, like Wino Grandi seems like untied embedding 16 layers performs so much better. Which makes me wonder what's so special about Wino Grandi. What's the data set? Wino Grandi. Who are you? Adversarial data set. Can we take a look? What's so special about it? Okay, John moved the couch. Okay, and we probably fill in the gaps, right? From garage.
It's more like grammatical reasoning, so like based on garage and backyard, both nouns there, which one fits the fill in the blanks?
Yeah, but like, what's so special about it that it just like I'm trying to figure out why this makes sense. And this makes sense only if the distribution of our input is significantly different than the distribution of our potential output, in my view.
Hmm.
So
Probably like the pre-training tokens, like in most cases favor more factual questions like Q&A data sets, and then here you have probably like a reasoning data set wherein like it's not straightforward and things like that. So the model typically flips there.
maybe, I'm not sure. I guess.
Could we
Well,
take a look
anyhow,
at the other data set just for comparison?
at other data sets, yes, sure. So
Yeah.
like, let's take a look at something where, well,
Any of them.
MMLU.
Yeah.
MMLU I know by heart, but probably not all of us do. So MMLU Pro, this is what you usually have. So you have some sort of a question, like it's questions in different groups, like biology, chemistry. So like subjects that you learn in high school and in university. And then you have questions with options, multiple options. Ignore this COT content stuff, it's meaningless. What's really meaningful here is the question itself. So like, let V be a set of all real polynomials. Like we have mathematical questions, you have questions on biology with lots and lots of options. And usually the way that they measure accuracy in MMLU, and I don't think we have. They don't tell us how exactly they measure the accuracy. Probably you can take a look at the code, but usually we provide the models with option answers like A, B, C, D, F, some numbers or letters, and ask the model to choose a letter or number. So I guess here we also ask the model to choose a letter or number, which I don't know. It feels fairly close.
It
How?
might be the case, maybe I'm wrong, but might be the case that for this data set we don't have words that are in answers existing in the queries, and that's why we have different distributions between input and output uh, spaces. We just don't have corresponding tokens in the input. Maybe.
All right. I don't know. At least, well, it's a mystery to me. If you have any other ideas, I'm all ears.
So in this case, during winner grant this benchmark, the tied one performs better than the untied. Whereas in all the other cases, it's the other way around. Is that it?
No,
Or
no, no.
No, it's
Like
vice
in
versa.
Vina Grande,
Untied.
untied
oh,
performs
okay, untied
significantly
performs
better,
better than okay.
which means that like the output projection for some reason like matters so much, like which means that the input distribution should be significantly different compared to output distribution. But like you only have to pick an option, right? So like which one fits better into this into the sentence, bottle or pan.
So we either have different tokens in the input and the output, or we have different embeddings associated with them, which means different projections. Sounds like
Yes,
a data issue.
maybe. Or maybe because it's binary. So basically it's binary here and all other data, like in MLU we
Yeah,
have many options.
maybe. Yeah.
In Hella Swag, what happens in Hella Swag? We have multiple endings, I guess. Like how many? Multiple, plenty of endings, right? So maybe because it's binary-ish? I don't know. Maybe. All right, anyhow, so apart from the Wino Grande, whatever you pronounce it, tied embeddings perform on par or even better than untied embeddings with the same number of layers, but the model is smaller. Wrapping up the tied embeddings and onto the intro to positional embeddings. So the original idea of positional embeddings was like, all right, they don't have this in the book, but one of the ways how we can do positional embeddings, and I think it's the way Karpathy presents it, is that you can have learned table with positional embeddings, right? So we can have a learned matrix, which LLM learns how to populate and how to apply positional embeddings-ish, in a sense, by kind of merging the embedded space with the positional space. But they didn't even present it as an option in the book because I don't think anyone uses it in production. So in production, what's been used for a long time, it's been absolutely positioned embeddings with, I think, the same sine cosine thing. And then, well, the idea is that like we have words, right? We have tokens, and these tokens, using sine, cosine stuff from the original paper, they encode it into positions. Lovely, boom, you add the positional embeddings to original embeddings, you have your LLM starts understanding the positions of the tokens. And a major limitation there was that once you go beyond what LLM saw before, it's kind of hard to, model can't really determine the relationship for the untrained indices because it's never seen them before. So they're not like relative, they are absolute, right? And what's been proposed, like with one of the ideas, like let's use relative stuff. So like let's instead of encoding absolute positions, let's encode like distances between different tokens. And in the book, they don't really present us with an option on how exactly you encode the distances between different tokens. But well, I guess you can encode different distances between different tokens. And they jump straight into rope. And I guess today, what I really want to highlight on the like a short intro to rope and what it is, and spare the deep dive for our next meeting. So like short intro to rope is basically, instead of adding your positional embeddings to your original embeddings when you kind of do the embedding projection, we do the embedding projection and rotate the vector, like rotate token vectors before before attention. So the residual stream is left untouched. In residual stream, we don't have any contamination of like the data by the positional embeddings. We encode positions only we go into this like kind of side stream when we do it where we do attention, and there like roughly the idea is basically all you need to know, well, all we need to know and all we need to remember is that like before the attention block, our Q and K vectors, they are rotated based on the like the position in the sentence relative to each other. So like they're rotated by a certain angle based on the position, and then the magic happens in the inner product of this two vectors. So when we do the inner product, well, this like R mumbo jumbo Q or R mumbo jumbo K. When you do the inner product, it's the transpose of the first stuff. And it's right here. Like I think Claude described it a bit better. So like this thing is basically the transpose of the first like part of the equation multiplied by the second part. And then when you do this, you end up with Q transpose in K. And this stuff like R transpose R, it can be shortened into R n minus m, which is exactly the relative distance between two tokens. And I guess this is the gist of it, and we'll have a much better deep dive in the next meeting. And I promised like that I'm going to keep this meeting short. So like if you have anything to add on rope here and now, I'd be happy to give you the mic. But this is it from me for today.
Yeah, sorry, I just joined, but no questions from my side if it's a basic rope.
Yep. I just wanted to kind of probably in the next meeting have kind of a much more detailed overview of rope. Especially it's just like somebody in the chat sent, like in the other chat sent that there's another study on rope saying that rope is doing not what we wanted it to do. And like in the book, they also give a short overview of no positional embedding. And I recently saw another study saying that compared to NOPE, doing no positional embeddings at all, we can start with positional embeddings and then we can remove them, and model still like performs like after a slight bump, model performs at the same level. So basically, positional embeddings are kind of training wheels, helping the model to learn. But once again, more papers are coming for the next call.
Wait,
Anything else?
what do you mean? Like you can remove positional embeddings entirely from the model and model will still be able to predict correctly everything?
Yeah, if you train it for a bit.
But how it understands the positions if the positional embeddings are removed?
I think the idea here is, well, I think it works only for decoder models. And then for decoder models, softmax is the key, right?
You mean,
so when you have two tokens and compare it to four tokens, softmax kind of scales them differently. So that's how the model learns the positions.
you mean it's no, it's not obvious for me.
Yeah, well, I'll try to
Like,
kind of take us through a better like understanding of why that research might have showed what it showed
no, I mean,
next time.
if you imagine a decoder model, for example, like without KV caching, without talking about it, well, KV caching doesn't do anything, but if you'll take a look, for example, at one layer transformer without positional encodings, and then for like the last token in the sequence, you won't be able to understand the positions of the tokens. And because of this, attention won't make any sense because, well, all positions will be equal for the transformer if you're talking about first layer. I believe that in later layers, the positional information might be extracted, but yeah, the problem is that you will have to spend some time to extract. I mean, you need to process several layers to extract this information properly.
Yeah, probably. But in that research, in that paper that I saw like a couple of months ago, probably when they do this additional training, that's exactly what's happening. So like later layers, they start encoding this positional information. And the way that I think about it is like going back to the screen. Let's try to do this. So when we're talking about causal masking, right? So this is like typical causal masking. Let me do this. Right, so this is the first token across encoded across multiple sequences, right? So and here, like because it's a single token, softmax is going to give it 1. So here it's going assuming that the denominator here is going to be 2, right? So like if tokens have equal probabilities, then equal scores, then it's going to be 1, 2, 1 half, 1 half. And here, given the equal scores, we're going to have 1/3, 1/3. So I think like this information that the same token across different sequences has different kind of weights and softmax. This is the key in a sense. But it's like my basic understanding, like intuition behind it. And I'm promised to have a much better detailed explanation for you next time. So this is like a sneak peek into my thinking. Does it make sense? Right. Hopefully it does, because like we don't have any objections. And once again, guys, please DM me in Telegram or Discord if you want to present, because I'm out of capacity for May. So unless we have volunteers to keep going, we'll have to put the club on hiatus until I successfully publish the paper and, well, not so successfully, who knows, and then have more time in June. So let me know if you have like any capacity and desire to do presentations in May.
I can do for the next few weeks. Probably I'll ping you in Discord about that, and also like best of luck for your paper.
Awesome. Thank you very much. Yeah, I'd be happy if you take over like at least for the next few weeks. So thank you for that.
Yeah.
All right. Then this is it from me for today, and best of luck and have a good Tuesday. And I'll stop sharing and stop recording.